Dear students, in this video we are going to learn about the concept of multiple linear regression. The objective of this video is to give the introduction about multiple linear regression, assumptions in regression analysis, problems in regression analysis, and improving the accuracy of the linear regression model. In multiple linear regression, two or more independent variables, that is predictors, are involved in the model. In the current example which we have seen in the simple linear regression, in the last section we came up with a simple linear regression by considering the price of the property as the dependent variable and the area of the property as the independent variable. That is, price of the property is equal to function of the area of the property. However, the location, floor, number of years of since construction, amenities available are important predictors which are not at all included in that model. Thus, if we consider the price of the property as an independent variable and area of the property, location, floor, number of years since purchase, and amenities available as the independent variables, then the multiple regression equation will become as follows. The price of the property is equal to the function of area, location, floors, aging, and amenities. The simple linear regression model and the multiple linear regression model assume that the dependent variable is continuous. The following expression describes the equation involving the relationship between two predictor variables, namely x1 and x2. So here two predictor variables are given, x1 and x2, and y is the dependent variable. The model describes the plane in the three-dimensional space of y bar, x1 and x2. Y is a dependent variable, x1 and x2 are independent variables. A is the intercept of the plane and b1, b2 referred as partial regression coefficients. So parameter b1 represents the change in the mean response corresponding to a unit change in x1 when x2 is held constant. Similarly, b2 represents the change in the mean response corresponding to the unit change in x2 when x1 is held constant. This is a change in the mean response corresponding to the unit change in x1 when x2 is held constant, that is b1. b2 is nothing but the change in the mean response corresponding to a unit change in x2 when x1 is held constant. Consider the following example of multiple linear regression having two predictor variables, namely x1 and x2. So the expression given is y bar is equal to 22 plus 0.3 into x1 plus 1.2 into x2. This is a sample in multiple linear regression model given, and this equation represents this type of plane. This plane is showing this equation. Y bar is equal to 22 plus 0.3 x1 plus 1.2 x2. So multiple regression for estimating equation when there are n predictor variables are there, then the multiple regression expression can be written as y bar is equal to a plus b1 x1 plus b2 x2 plus b3 x3 so on up to bn xn. Here this is b2, this is b3, this is bn. While finding the best fit line, we can fit either a polynomial or curvilinear regression. Assumptions in regression analysis. Here the dependent variable y can be calculated or predicted as linear function of the independent variables plus an error term that we have already seen. For example, y is equal to a plus bx. That is simple linear regression. In multiple linear regression, y is equal to a plus b1 x1, a plus b1 x1 plus b2 x2. So like that, here you have set of independent variables x1, x2, x3 like that up to xn, and one dependent variable y will be there, and one error term epsilon will also be there. This error term represents the difference between the predicted value and the actual value. The number of observations n is greater than the number of parameters. So that is the another assumption that is made in the regression analysis. Relationships determined by regression are only relationships of association based on the dataset and not necessarily on the cause and effect of the defined class. Here, the relationship is based on the dataset, not on the other parameters. Regression line can be valid only over a limited range of data. That means if you train the model on a limited range of data, it will perform well for that model. If the line is extended outside the range of extrapolation means beyond the range of the data used to build the model. So beyond the range of data used to build the model, then it may lead to wrong predictions. So if you train the model with certain range of data, it performs well. If you use that for the data which is beyond the range, then the model will give you wrong predictions. If the business conditions change and business assumptions underlying the regression model are no longer valid, then the past data set will no longer be able to predict the future trends. For example, in stock market, if you assume that, so what are data used in the past, that may not be correct in the present scenario because there may be change in the conditions in the business and the assumptions of the business are longer valid. So that's the reason the past data may not give you the correct predictions for the future trends. Variance is the same for all values of x. The error term is normally distributed. This means that the mean of the error has expected value of 0. So that is very simple. So normal distribution mean generally it is 0. So therefore, if the error term is normally distributed, automatically the mean of the error term is also 0. The values of the error are independent and are not related to any values of the x. Of course, this is true. So because the error is independent, it is not related to any values of x. This means that there are no relationships between the particular x and y that are related to another specific values of x, y. So there is no relation between one set of xy with another set of xy. So that's the reason. So error values are independent and are not related to any values of x and y. The main problems in regression analysis is, in regression analysis we have two problems, that is multicollinearity. Another one is heteroskedasticity. What is meant by multicollinearity means two variables are perfectly collinear if there is an exact linear relationship between them. For example, in our house price quote problem for a house, if you consider two parameters like the rooms, number of rooms and the size of the house, they are related to each other because if the number of rooms are increased, it might increase the size of the house also. Similarly, if the size of the house is increased, the number of rooms are also increased. So that kind of relation will be there between the independent variables also. So that is one of the consideration in multicollinearity. Multicollinearity is the situation in which the degree of correlation. Multicollinearity is the situation in which the degree of correlation is not only between the dependent variable and the independent variable, but there is also a strong correlation within the independent variables themselves. So that's what I have explained, the rooms and the size of the house. So correlation means they are related. A multiple regression equation can make good predictions when there is a multicollinearity, but it is difficult for us to determine how the dependent variable will change if each independent variable is changed one at a time. So it is the another difficulty with the multicollinearity problem. That is how the dependent variable will change if the independent variable is changed one at a time. It is very difficult for us to identify this. When multicollinearity is present, it increases the standard error of the coefficients. By overinflating the standard errors, multicollinearity tries to make some variables statistically insignificant when they actually should be significant. One way to gauge multicollinearity is to calculate the variance inflation factor VIF, which assesses how much the variance of the estimated regression coefficient increases if the predictors are correlated. If no factors are correlated, the variance inflation factor will be equal to 1. So these are all the problems with the multicollinearity property. To address the multicollinearity, some possible solutions include removing or combining the variables, regularization techniques, principal component analysis, gathering more data. So if two or more variables are highly correlated, it might be appropriate to remove one of them from the model or combine them into a simple composite variable. This is the technique suggested by removing or combining the variables. So we might remove one or more number of variables if they are related, or we combine them into a single composite variable. Another technique used for eliminating the problem with the multicollinearity is regularization technique. In regularization techniques like ridge regression or lasso regression, we can help to mitigate the impact of multicollinearity by penalizing the large coefficients. Penalizing the large coefficients means it may be like removing the large coefficients. Principal component analysis, PCA in short. It can be used to transform the original variables into set of orthogonal components. So what is meant by orthogonal components? Making the related coefficients into uncorrelated components. That reduces the multicollinearity property. Gathering more data. In some cases, due to the limited range of data availability, the correlation may arise between the variables. In that case, we will try to collect more data pertaining to that data set or problem, such that we can reduce the effect of multicollinearity problem among the variables. Addressing the multicollinearity is crucial to ensure the reliability and interpretability of the regression model and its coefficient estimations. Heteroskedasticity. It refers to the changing variance of the error term. If the variance of the error term is not constant across the datasets, there will be erroneous predictions. So therefore, the covariance of the error term must be constant. Then only it means that the model is well trained and it will try to predict the values more accurately. In general, for a regression equation to make accurate predictions, the error term should be independent and identically distributed. So identically distributed means the error term will have the mean value 0. Mathematically, this assumption is written as variance of ui given x is equal to sigma square, where u represents the error term, x represents the independent variable. Covariance of the two error terms ui and uj, where I is not equal to j, given x is equal to 0. This assumption is more commonly written as variance of ui is equal to sigma square, covariance of ui uj is equal to 0. Improving accuracy of the linear regression model. Let us understand the bias and variance in regression model before exploring how to improve the accuracy of the linear regression model. The concept of bias and variance is similar to accuracy and prediction. That means bias means accuracy, variance means prediction. What is accuracy? Accuracy refers how close the estimation is near to the actual value, whereas prediction refers to continuous estimation of the value. What is meant by high bias, high variance, low bias, low variance? High bias means low accuracy. That means it is not close to the real value. High variance means low prediction. That means the values are not correctly predicted, they are scattered. Low bias means high accuracy. That means it is close to the real value. Low variance means correct prediction, high prediction. Values are close to each other. So that is the meaning of high bias and high variance, low bias and low variance. So it is always preferred to have highly accurate and highly predictive regression model. Therefore, the overall error of our model will be low if you have low bias and low variance. This is highly preferred combination of bias and variance in the regression model. Similarly, we can say that if the variance increases means low prediction. The spread of our data points increases, which results in less accurate prediction. Similarly, as the bias increases, the error between our predicted value and the observed values increases. Therefore, balancing out the bias and accuracy is essential in a regression model. Low bias and low variance is the preferred combination in a regression model. In the linear regression model, it is assumed that the number of observations n is greater than the number of parameters k. N is number of observations, k is parameters. Observation means collected data, collected samples. K means number of parameters in the given problem. That is, if n is greater than k, in this case, the least square estimation tends to have low variance and hence will perform well on the test observations. However, if observation n is not much larger than parameters k, then there can be high variability in the least square feet, resulting in the overfitting problem, leading to poor predictions. That means if n is greater than k, we have correct predictions. If n is less than k, then the model cannot be properly trained, so it will give you poor predictions. K is greater than n, then linear regression is said to be unstable. This also indicates infinite variance, so the method cannot be used at all. Accuracy of linear regression can be improved by using the following three methods. One is shrinkage approach, subset selection, dimensionality reduction. Shrinkage approach is nothing but regularization approach. In this shrinkage approach, we limit the estimated coefficients. That is, we try to reduce the variance at the cost of negligible increase in bias. This can in turn lead to substantial improvement in the accuracy of the model. Few variables used in the multiple regression model are in fact not associated with the overall response and are called as irrelevant variables. This may lead to unnecessary complexity in the regression model. So that is, if you take a problem, some of the variables are not going to influence the overall response of the problem. So they are said to be irrelevant variables. Such irrelevant variables can be eliminated. So we can reduce the variables by using this shrinkage approach by identifying these irrelevant variables. So this leads to substantial improvement in the accuracy of the model. This approach involves fitting a model with all predictors and the estimated coefficients are shrunken towards zero. relative to the least square estimates. That means if you assume that y is equal to a plus b1x1, b2x2, b3x3, like that, you have some of the independent variables in the multiple linear equation. Then what happens? Some of the coefficients are made 0 so that the effect of the corresponding independent variable can be eliminated. So that is, this point says estimated coefficients are shrunken towards 0. Some of the coefficients are made 0. This shrinkage has the effect of reducing the overall variance. So some of the coefficients may be estimated to be exactly 0, thereby indirectly performing the variable selection. For example, if we understand that y is more dependent on x1 rather than x2, in that case we can eliminate the impact of x2 in the prediction of y value by making b2 as 0. So when b2 becomes 0, this entire product will become 0. So when this term will become 0, then automatically its effect in the final prediction process will be 0. So in that way we can reduce the sum of the in that way we can make variable selection. The two best known techniques for shrinking the regression coefficients towards 0 are ridge regression, another one is lasso regression. Lasso means least absolute shrinkage selection operator. By using these techniques, we can make how to make coefficients towards 0 can be done. In case ridge regression performs L2 regularization, that is, it adds penalty equivalent to square of the magnitude of the coefficients. That is, the minimization objective of ridge is equal to least square objective plus alpha into sum of square of the coefficients. LS OBJ is nothing but least square objective without regularization. After regularization, it becomes least square objective plus alpha into sum of squares of the coefficients. Ridge regression is very similar to least squares, except that the coefficients are estimated by minimizing a slightly different quantity. One disadvantage with ridge regression is that it will include all k predictors in the final model. This may not be a problem for prediction accuracy, but it will be a problem when there are more number of predictors k. Ridge regression will perform better when the response is a function of many predictors, all with coefficients roughly equal to size. Lasso regression. Lasso regression performs L1 regularization by adding the penalty equivalent to absolute value of the magnitude of the coefficients. So therefore, the minimization objective of the ridge will be equal to least square objective, that is before regularization, plus alpha into absolute value of the magnitude of the coefficients. This lasso regression overcomes the disadvantage of ridge regression by forcing sum of the coefficients to 0. Making sum of the coefficients to 0 is called as sparse model, and this sparse model will be simple, more interpretable. The lasso model can be expected to perform better in setting where a relatively small number of predictors have substantial coefficients and remaining predictors have coefficients that are very small or equal to 0. So some predictors have substantial coefficients. Some predictors are having very small coefficient or equal to 0 coefficient. Subset selection. Identify a subset of predictors that is assumed to be related to the response and then fit a model using OLS, where OLS is nothing but ordinary least square on the selected reduced subset of variables. There are two methods in which subset of the regression can be selected. One is the best subset selection method. Second one is stepwise subset selection method. In stepwise subset selection, we have forward stepwise selection model and the backward stepwise selection model. Best subset selection. We fit a separate least square regression for each possible subset of k predictors. From that subset of k predictors, we will choose the best one. This model will be suitable when the k value is less, but for computational reasons, this best subset selection model cannot be applied when the value of the predictors k is large, because the best subset selection procedure considers all 2 power k possible models and then selects the one which is the best among these 2 power k models. Stepwise subset selection model is also used to choose the best subset. It follows the two methods. One is forward subset stepwise selection model. Another one is backward stepwise selection model. In the forward stepwise selection model, it will start with the smaller subset and it increases one by one predictor, and it finds out a model that includes the predictors that gives the more accurate predictions. So, forward stepwise selection begins with a model containing no predictors, and then predictors are added one by one to the model until all k predictors are included in the model. At each step, the variable x that gives the highest additional improvement to the fit is added. Whereas in the backward stepwise selection begins with the least square model, which contains all k predictors and then iteratively removes the one by one predictor until none of the predictors are included. And finally, it will choose the predictors that gives the best prediction accuracy for the dependent variable. Next one, dimensionality reduction. The earlier methods, namely subset selection and shrinkage method, control variance either by using a subset of the original variables or by shrinking their coefficients towards the 0. In dimensionality reduction, the predictors are transformed and the model is set up using the transformed variables after dimensionality reduction. The number of variables is reduced using the dimensionality reduction method also. Principal component analysis is one of the most important dimensionality reduction technique. Thank you for watching this video.